Okay, yeah. So, welcome back to the reading group after we had a month-long break or so. So today we're going to start, on a new set of 10 papers that will take us, somewhere like through, I believe, June, so mid-summerish or so. And the paper we're going to discuss today is called Perseus, a fail-slow detection framework for cloud storage system. So this paper is from recent FAST 23. It is a deployed system paper. So, the stuff that we're going to talk about is like real, actually deployed in production, and has been used for 10 months at the time they had the paper out. So like probably more than a year at this point. Let's talk about slow failures first, right? So kind of traditionally, when we think about distributed systems, we want them to be fault tolerant, right? And kind of the more traditional fault tolerance models, they would assume something on this side, like machines failing or network failing, and the failures are kind of almost binary, right? So they either happened or they didn't happen. Right, and we'll use failure detectors of some kind to detect this binary fail, non-failed state. And if we make a mistake sometimes, I guess it's okay, right? We can reconfigure and whatnot. But the state tends to be like more or less binary when it comes to the failure. Now the slow failures, they are somewhere in between this kind of completely failed state and a normal, like healthy state of a system or of a server or whatnot. And it can manifest itself as just something working slow, right? So I put a turtle here to kind of show that this is maybe a slow server, right? So and this is kind of the problem with detecting them. Like, how do we detect these slow failures? How slow is slow, right? So if we have this kind of binary model of failed, not failed, it's easier to make those detections, or easier to decide. But here, like, at what point do we consider something slow enough to be slow, right? And the authors of this paper, they had this problem. Like they explored some of the prior attempts that they've tried on detecting this type of failure, and they were playing with things like thresholds, right? Like trying to set a threshold. Maybe if something takes longer than certain amount of time, this is going to be a fail slow event, and we'll designate this component, machine, or whatnot as fail slow. But it doesn't work this way. Like, you need to somehow set those thresholds, and they will differ from system to system. They will differ from different types of hardware, different models, different manufacturers, and so on. So setting those thresholds is kind of very cumbersome, error prone, and requires a lot of like human expertise, right? So another problem that we kind of want to look at is at what kind of granularity we look at these fail-slow problems, right? Are we looking at fail-slow data center, fail-slow rack? Are we looking at the level of maybe servers or virtual machines, nodes? Or are we going down into like even finer components, like slow hard drives or slow SSDs? And according to the authors, a lot of the existing literature, it focuses more on like server and node level, right? But for their use case, which is storage, they really want to focus down to identifying like failed components within a server. And that's because in one like storage server, they'll have multiple SSDs or multiple hard drives, and like everything may be working just fine except for one slow SSD, and this one slow SSD or hard drive will cause that particular server, that particular node, to maybe experience high tail latency. right? So those kind of slow failures at the component level, they show themselves as higher tail latency, which may be like more difficult to diagnose and to find. So that's kind of the problem that the authors of this paper were after. Like they wanted to know not just like what server potentially has a fail slow problem, but maybe what component, like what SSD or what hard drive within that server is the culprit. To kind of illustrate this, I borrowed this figure from the paper, right? So they have, in this example, they have storage server that is, working and experiencing high tail latency at the, P95, P99, and P99.99 percentile, right? So, the tail latency is high, but the median latency and even P9s, like 19th percentile latency, they all appear to be normal, right? But just some high tail latency for whatever reason, and they actually identified a failed drive on this machine, on this server, and removing this machine, removing this failed drive from the server brought down the tail latency, right? So if we can identify those slow components, we don't need to decommission the entire machine. We can just decommission a drive, replace it and whatnot, and fix the problem. So that's kind of the motivation why they go down into that component level, why they look at the fail slow drives in their like storage infrastructure. And the approach that they take, it really like looks at this latency and throughput data, right? So for each disk, for each drive, they collect the latency and throughput as a time series data, right? So they at a specific time they know what was the latency of the operations there, write reads and whatnot, and what was the throughput that this drive was doing. You can kind of visually plot this data as latency versus throughput. So you can expect, and this is something that they found, through their like previous not so successful attempts at figuring out the fail slow drives in their clusters. But you can plot this data and visually see that at the low throughput, the latency tends to be lower, and as the throughput increases, because of like queuing effects and whatnot, the latency also increases. But that's all normal behavior, right? However, they also see that failed drives, they don't fit this like normal curve, right? So they appear as outliers. So if you plot this data, if you visualize this data, you'll have like majority of data points, fitting, this kind of nice pattern, and then you'll have some outliers. And these outliers, they can potentially indicate a fail slow drive. And they do this kind of latency versus throughput analysis at the per machine level, right? So this is unique for each machine that they have in the cluster. So this is kind of the raw data. They collect latency and throughput, and from this raw data, the first thing that they do is they do the outlier detection, right? So if there are some data points that the minority of data points that don't fit the general pattern, they use clustering technique, the clustering algorithms, to find those outliers and kind of set them aside for now, right? So they look at the main cluster, right, of data points that's supposed to represent the healthy drives and how they performed in that particular storage server, and they do a regression model on this data, right? To they feed a curve essentially to figure out what is the expected latency and throughput for a healthy drive, or healthy disk or SSD. From that regression, they also compute an upper bound, which I think is like 99.9 percentile or something. And everything above this upper bound, they identify as slow records. So these slow records are indications of potential fail slow, drive or fail slow event in the system. So that's really the basics of this Perseus systems, right? Look at the storage server, get the data on latency and throughput from all of the drives, find the outliers, filter them out, fit regression to this data, and then look at those outliers again, essentially. So yeah, now there is a little bit more to the system. So once they have that regression model, they actually start looking at the data again, kind of go through the time series that they have, and for each this outlier points, they calculate the slowdown ratio, right? So is it like a big slowdown, like a significant event, or maybe not so significant? And from the slowdown ratio, they and essentially slowdown ratio is allows them to tell, hey, do we classify this event as fail slow or not? Right. So if the slowdown ratio exceeds some threshold, which they set, then it's considered a slow event, and they actually have like a different classification of slow events, like borderline slow, like normal slow, like really bad slow, and depends on how slow that slow event is. They actually compute the risk score, right? So they rate each drive by this score, and the drive with the highest score is like more likely to be the fail slow drive. And at this point, the manual intervention is required. They, have engineers go and inspect, the drives that have the high score, and maybe take them out and, see if tail latency improves. So, they've been using this in production, and the paper has quite a lot more data on this, and it's all quite interesting. But they also with their production data set, which they also published online, they did the evaluation that compared their, so these three columns, the first three columns are their previous attempts that were not so successful, and this IASO-based is another system from literature that they have re-implemented, for the sake of comparison, and obviously Perseus, right? So if you look at precision recall, this Perseus system that they built, beats pretty much everyone else. So I think I'll stop at this point, and maybe we can do the discussion.